All right, class, let's begin. Let me hide this stuff here. Okay, 5.5, this is the last section of chapter 5. So far, if we've been thinking about it, we've been looking at the normal distribution. We looked at how to find probabilities beside the normal distribution. We found how to go backwards. We found how to find the z-score and back to the x value. So forward, backwards, 5.4 was all about finding or understanding that we can turn pretty much any data into a normal distribution, or better yet to say it is, we can approximate any data by normal distributions. So as long as, I think the thing was, as long as n is greater than or equal to 30, right? As long as we take 30 samples at a time, that we can do that. Or that we know it models already a normal distribution. That's kind of your two. Okay, 5.5, the question is this: how do you find things that only have two answers, like success and fail, heads or tails? That's kind of what we're looking at. So you're looking at a thing that is not set up for continuous distribution. And so now let's see what happens here. And so first things first, lots of writing here. So notice now it's called normal approximations to binomial distributions, right? So the normal distribution approximates our answers. Okay, lots of writing, lots of stuff as we begin. So let's go with it here. So I'm going to go all the way down the list so you guys know what you're writing. And then we'll jump to specific examples here. So first things first, what do we find out? Just like our sample size of 30 or greater, this one also has condition. So the conditions are this: n times p, so the probability of success times the number of sample size that you have. If you multiply those together, it has to be greater than or equal to 5. Then the number of the sample size times this your fail rate. When you multiply those together, those have to be greater than or equal to 5. If you do that, then you can approximate the data by a normal curve. Then we go down. The mean is going to be n times the probability of success. That's an easy one. Remember, the mean was for continuous function. It was just the mean of the average that was before, right? This one has just one little multiplication symbol here. Standard deviation here, instead of standard deviation of the population divided by the square root of n, now it's the square root of n times p times q. All right, n is the number of trials instead of sample size. P is the probability of success, and q is the probability of failure. All right, so with that stated, let's kind of just do this. First of all is kind of to think about the little 5 and 5 condition. That's one thing to think about. Second thing is to think about graphically, how does this change? How does this move to actually approximate normal distribution? So let's check this out, just as a graphic illustration here. And I believe this is in the textbook itself here. So this one right here, let's think about a probability of 25% being success. That means 75% is non-successful. And let's say our n size is 4. So, and then let's look at n size of 10 and then 25 and then 50. Let's kind of see how that works. So no, if you have n is equal to 4, notice the multiplication of n times p and n times q, it's 1 and 3, that would surely fail. And does that look like a normal distribution? Not at all, right? It's super duper skewed right. Okay, so then if we move on to n is equal to 10, and not quite there yet, and look at our numbers, 2.5 and a 7.5. So one of them fails, the top one fails. Then we look at 25 trials. This one. Now it's like, oh yeah, no, I could see, yep, it is kind of forming out to be That's pretty good. What do you guys say? That's pretty good. Kind of normal. And then if we can we go any further? Absolutely. We go something like this. That's going to be even a better approximation. So yes, even if with the 25% success rate and a binomial distribution changes into at least approximated by continuous distribution. That's what we're looking at here. All right, let's jam with our problem then, or two problems here. So two binomial experiments are listed. Here it is. Determine whether you can use the normal distribution to approximate the distribution of X, the number of people who reply yes. And if you can, then find the mean, find the standard deviation. But if you can't, tell me why and why not. So it goes to that little condition of 5. We good? So all yours here, this is the condition of 5 is met. So you guys get to calculate that. So I'm going to read it here for you. The survey of 8 to 18-year-olds are heavy media users in the United States. And I don't know what the heavy media users, what the definition of that is, right? We don't even know. Usually it's like so many hours per day or something like that. All right, 47 said they get fair or poor grades. You randomly select 45 8 to 18-year-olds, heavy media users in the United States, and ask them whether they get fair or poor grades. Now, with stats, this would have to be quantified quite a bit, right? What does heavy mean? Heavy media user mean? What does it mean to have fair or poor grades? Or right here, actually does say C or below, okay? So question is this: if you take a whole bunch of time to hear media, does your grades go down? That's trying to at least set up the correlation there. All right, you guys, all yours, go for it. You guys talk to me. Does this qualify So the first setup would be n times p, is that right? And n times q. That's the first setup. And if it passes, then we can keep on going. So I'm going to jump to this here. So in the binomial experiment, 45 is equal to n. Is that right? P is equal to 47, Q is equal to 53. Let's multiply those guys together. What does that make? $21.15. I agree with that. 21.15. Perfect. Okay, so one condition is met. Is the other one met? And you can kind of tell whether it's going to be met because notice 45 is going to stay the same, right? We're going to switch from 0.47 of 47%. We're going to switch it to 53%. Obviously, that number is even going to become bigger than 21.15. So we got a 23.1. Yes, perfect. Because NP and NQ are greater than 5, now we can use the normal distribution. So let's practice that formula. So how do we get the average again? What's the mean? It's the same. Perfect. It's already given. Once you calculate the n times p, you already calculate the mean to go on. So just shift it down 21.15. All right, the other one we have not calculated yet. It's the square root of n times p times q. So the formula given, all yours to give me the answer. Perfect. Yep. 3.348 or 3.5 would be just fine. So there it is. Just the formulas themselves first and foremost, just to make sure we got that. All right, all yours writing it down. All right. Now let's look at the graph of this guy. Okay, if we did use 45, because 45 is a pretty large number, and 47% and 53%, the graph of it pretty much looks like this. Is that pretty close to a normal distribution? I would say so. That is pretty close there. It's almost symmetric there. Okay, so now let's go another way here. So number 2, all yours. Can you get these numbers right here? Survey of 8 to 18-year-olds. Heavy media users. And now at this point, 23 say they have fair or poor grades. All right, what we're gonna do is we're gonna randomly select 20 8 to 18-year-olds in the United States, ask them whether they get fair or poor grades. Interesting. So in both cases, one was 47%. Now this is 23%. Seems to indicate the opposite, right? As you listen to media or have stock media, seems to be the opposite. You do get better grades. All right, well, let's jam. Hopefully you guys have got those already here. I got myself. Let's see. N times P turns out to be 4.6, huh? Shy of 5. That's not cool. All right. And then N times Q, that point is 15.4. That one's fine. Just at 4.6. And that's the problem is both of them have to be greater than or equal to 5. So because NP is less than 5, we cannot use a normal distribution. And then also, if you look at it, it also does not look all that great. It does not look like a normal distribution. It's, if you think about it, it's kind of slightly skewed to the right, if you want to think about it. So there you got an average of 4. 4 goes down to 0, but 4 goes out to 10 from the right-hand side, and it keeps on going. So slightly skewed to the right on that one. Okay. So let's see, we got the formula, is that right? No, we got the condition, and we have the 2 formulas. That's cool. One more thing we got to think about with continuity is the fact that whenever we deal with binomial pieces, we have specific numbers in place. So let me talk to you about that, and we'll talk about how do we correct it here. So first things first, a binomial distribution is discrete. Is that right? How many phone calls you make in a day? That's a discrete piece. We're good? And so what we want to do is we want to be able to go from a discrete data into continuous data. And so if we talk about discrete data, we're kind of looking at just that little C right here, value only. If we're talking about continuous data, we're talking about the area underneath here. And so what we do is, we've seen this before, we're going to add an extra little piece to that C value. And we're going to do something called the class borders. You guys remember those, the class boundaries from chapter 2? We're going to expand this out so that it hits the boundaries each time. So if our values are integer values, all we're going to do is we're going to add a 0.5 to C, and we're also going to subtract 0.5 to C to fill it in. So now, since it's filled in, now it's technically continuous data. Okay, we're good there. So we add a half a unit at each side by adding half a unit, and that's really just to get us to that area stuff. So once we get a z-score, once we look at the table, so we have a fitted in values. Okay, so let's talk numbers here, just to make sure that we understand it, we get it. So let's see, don't have to write stuff down, just kind of think with me on these next two problems here. So first things first is this one right here. So use a continued correction to convert each binomial probability to a normal distribution. So here it is, the probability of getting between 170 and 310 successive trials. So if we think about that, if you say, I want to get to the borders of 270 and 310. Boom. So if we kind of think about something, I'm not sure where the 270 is or the 310 is. I'm just going to put on both sides. If I'm looking from here to here, correct? And those are specific discrete pieces, right? I want to be able to include the whole 270 in a sense, right? So I'm going to go just a little bit below it. And so what do you guys say? What's the marker a little below 270? 69. Perfect. We're good there. We're just going to go a little bit lower to fill in that extra half unit here. And the 310, we're going to go 310.5. So now what we've done is we've kind of made it into a continuous approximation for area. And so if you want to write stuff down, that'd be something like that. That'd be a better sort of way of you doing it. All right, says it the way the book says it. Let me do it like this. Read between the little lines here. So discrete midpoint values of 270, 271, all the way to 310. We can do is we take the half value down from 270, half value up from 310, and we get ourselves a probability of 269.5 up to 310.5. So there it is. We've corrected for that. Okay, are we good there? Let me erase these things so they're not in the way. Okay, next one. Very similar here. How about this? What's probably getting at least 158 successes? So 158 heads on a coin toss. Probably of getting 158 answered phone calls, 158 sales using a certain script. All right, let's do the same here. Let's correct this for continuity here. So getting at least 158 successes would mean the probability of X being greater than what? All right, if we want to graph this little guy right here, right? So I have like this. Again, I don't know where 158 is. I'm just going to just kind of plop it down right here. Yeah, we want the area going above that, right? That's kind of what we want. So to include the whole piece of 158, we're going to kind of round it off right here, 157.5. So we are including that whole piece there. Okay, so the question is, do we always include the half units in our numbers? No, not really, not always. So let's take a look at that. Let's take a look at another one here. This is kind of, will give us a different perspective here. Let's see this. The probability of getting fewer than 63 successes. So in probability, we talk about, does it involve the midpoint? Does it include the midpoint? Does it not include the midpoint? That's kind of what we're sort of seeing. Does it include the value? Does it not? Does it include the C value? Does it not? And so let's go right here, boom, and go like this. And again, I have no clue where 63 is. I'm just going to put it right here. So in this case, what's the probability of getting fewer than 63 successes? So then what's my border here? So we want fewer than, right? Yeah. So if I want to go fewer than 63, and here's the weird punchline, I'm trying to go this way, right? I'm trying to get less than the 63. My border for 63, right, expands to 62 and a half or 63 and a half. But if I want less than 63, my border is going to go this way. I'm not going to include the 63. I'm not including the C value. So I'm looking at the probability of X being less than 62.5 this time. Are we good? Right, because the border of 63 is 62 and a half. And so let's kind of think our way back to number one if we wanted to. Number one number two. Number two included the 157 and a half, right? And it was just because of the wording. So notice it says, what's the probability of getting at least 158, right? If the wording says, what's the probability of getting more than 158, we would have not included the C value. So it's all about wording. All right, so sort of helpful kind of bit in the textbook, which you should probably refer to. Let me get to that in just a second here. All right, guys, good with that? Just want to make sure. So I want to turn you to the one that's kind of like the page that's the useful one here. So let me jump to that one, and then you guys can probably write that, and that'll be easiest one. This one right here, 277. If you want to write down page 277, the wording in English will dictate whether you're including the C or not including the C. Okay? So if you say find exactly C, what we do is we just find the border between C and, so we go up and down a half unit. If you say at most C, I want at most 36 successes or 63 successes. That means you do want to include the C. That means it comes up, includes the value. But this one right here, if it says fewer than, just like the last one, number 3, it says fewer than 63 successes. Notice you don't include the C because you want to go less than the number. Same thing happens on the plus side. If you say at least C, at least 158 successes, you include the C. But if you said, I want more than 158 successes, you would take off the C value, just do the border. You would do the upper border of that. Okay, hopefully that made sense with the examples that we did. Okay, so we're gonna practice a little bit more, especially going with kind of like the full measure of things here. I think I have three problems here as we go through. Oh yeah, okay, set it up already. All right, let's go back to our little heavy media user problem here. And so this is 47%, and we're looking at 45 trials technically, or users that we're going to ask. Yeah, this one did pass the 5 and 5 rule. Is that right? Let's go walk through it again, just because we have a new person in our class here. So let's go. What is the probability that fewer than 20 of them responded yes? Okay, so we're going to put this all together. Let's go. So 8 to 18-year-old heavy users in the United States, 47% said they get fair or poor grades. You randomly select 45 8 to 18-year-olds that are heavy media users and ask them whether they get fair or poor grades. What's the probability that fewer than 20 of them respond yes? Let's go for it. So condition set is this. Oh, okay. Go back if we're even going through a little piece here. One second, let me look at something real quick here. Let me go back to what we were talking about, the condition of met, because this is the way you're going to do your homework here. So let me go back to right here. When we did this the first time in the beginning, well, there's a little condition that the multiplication of your users or the number of trials, right, times your success has to be greater than or equal to 5. And your, I'm in the wrong one. There it is. Here's where we started off from, right? So this is the way you would probably do your homework here. So you look at this here, you look at 47%, you look at the fact that there's 45 users. So there's technically 45 trials you're going to do run. And you want to make sure that when you multiply them together, right here, N times P, your number of trials times your success, number of trials times your failure rate, they both have to be greater than 5. And if they are, then we go on to this step right here. We're good. And so as we are repeating the problem here now, 47% of them said poor grades. Yep, there's 45. So the conditions have been met. We good from the work that we did in the beginning of the chapter. Next, can we approximate it by a normal curve? Absolutely. And so we have the average is 21.15. Standard deviation is 3.35, which we calculated last time as well. So this is from last time. So now let's kind of get into this little 20 aspect right here. So what if the probability that fewer than 20? So fewer than 20, talk to me. Is the cutoff 20.5 or 19.5? I want fewer than 20. I want less than 20. I'm thinking as well, the same thing, right? Because what we have, you have bell-shaped curve. Oh, now I know where the 20 sits now, at least. This is 21.15. So 20 is about right over here. I want less than that. So it's going to be just not even quite to 20. It's going to be this little piece right here, half a unit shy. Okay, so hopefully we did enough work on that here. So there it is. The probability of X being less than 20, we're going to subtract half a unit away. So really we're looking at probability of 19.5. Okay, so now, just like we normally do, we have a normal distribution. We convert to z-score. We find probability. That's it. We've been learning that in chapter 5 all along. So let's go with it here. Mu is 21.15, standard deviation 3.35, and the shape we want to the left of a 19.5. So find the z-score, go for it. Here's your formula. Tell me when you got it. So let's do 3. Let's do 3 of these. This would be a good example. Let's do a left-handed set. Let's do a right-handed set, and let's do a middle set. All right, and then tell me also if you need help with your calculator. I will do that too. Hopefully you have your calculator with you as we'll do these. All right, tell me the z-score when you get it.
1,493.
Perfect. Okay, so real quick here, you know it's going to have to be a negative because it's on the left side of our average, right? So you know it's going to be negative. So 19.5 minus 21.15 divided by 3.34, negative 0.49-ish. Z-scores are usually 2 units always, but that's the way our table is made. Okay, awesome. So you can do it by table. If you want to do it by table, you're going to find out a 0.3121. That's the table in the back of your textbook. If you did it by, let's see. All right, let me bring up my calculator real quickly here. So how do we do this by calculator? So we get this by the table, 3121. And we practice how to do that by table. That's fine. Want you to do this by calculator here. So we're going to go to distribution. So second function over here. And all right, those with calculator, let's go for it here. So second function and distribution. And let's go to number 2. It's the normal curve distribution function. Clicking on that. And you have a 284, you're going to get to a different screen, right? It says lower, what does it say? Lower value or something like that?
Yeah.
Since we're going off to the left, our lower value is going to be like negative 1,000, negative 10,000, negative 100,000, whatever. You just want to go super low. Okay, comma, we're going to go up to a negative. Now, careful, this is your negative button. That's your subtract button. Those are 2 different buttons. So don't use the subtract button, use the negative button, negative 0.49. Comma to separate those. And now we're going to go with our standard curve, standard normal curve mu or average, and a standard normal curve standard deviation, which is 1. So 0, 1. And click enter. And let's see what we got. We get ourselves a 0.31206. So really 1. So it does correspond to that. So roughly 31%-ish. All right, boom, there it is. So probability that fewer than 20 8 to 18-year-olds respond yes is approximately 31.21%. Okay, that's the left hand value of it. Let's do another one. So going from beginning to end, are we good? All right, see if you guys can do this here. I'll even pause it for you guys to finish up. So let's see if you guys can go from beginning to end. A study of aggressive driving found that 47% of drivers say they yelled or have yelled at another driver. Whoa. Show of hands here, how many in traffic have ever yelled at another driver? You, no, you guys are all saints here. Nobody, nah. Oh, no, okay. 1.
Well, I mean, probably not at them, but you
Right, yeah. Uh-huh.
it's like that's
Yeah, so I'm not sure if they yelled so the person actually heard them, like actually yelled at them, or versus yelled in the car knowing that they didn't hear. I'm not sure what the proper definition for the study is. It looks like it's a true source. So American Automobile Association, that's actually true data. All right, you randomly select 200 drivers. Ask them whether they have yelled at another driver. What is the probability that at least 100 drivers say yes, they have yelled at another? So again, the word at least, think about that. Think about your correction for continuity. And I'll give you guys about 2 minutes, 3 minutes here. Can you go from beginning to end? So let's see, first things first is find out if you have met your condition, n times p, n times q. And if you have, then find your mu, which is your average, and then find your standard deviation. Cool. And then from there, find the z-score. Then from there, find the probability. Okay, I'll pause, give you guys about 2-3 minutes. All right, so let's jam with it here. So first things first, n times p is 94. And then n times q is 106. We fulfill the criteria. It's this criteria, right? Of being greater than or equal to 5. Next is the easy stuff is the n times p, that 94 that we got before is the average. So that's cool. So we can bring it down. It's the same thing. Standard deviation has a little slightly different formula. There it is. It's just the square root of the n and the q and the p all multiplied together. Anybody, what's the value for that you guys got? 0.06. I agree with that. Good. Okay. Boom. Okay, and now that's cool. Now we got to figure out what our x value is. So let me go back to what we said. What's the probability that at least 100 drivers will say yes? At least means we're going to the right this time, right? Are we including the c value or not including the c value? So choice really is, I'll graph this out. So there's 94 here. 100 is right here, right? So at least, the word at least. Does it include the 100? So we're going to tack on the 99.5 and then go forward? Or are we going to stop at 100.5 and then go on? So the word at least, does it include the 100 or not include the 100? Page 277 in the textbook, huh? Go for it. What does page 277 say? At least means, yes, you include the c value in your approximation. At least means this and then more. If you didn't want to include it, then you would say more than 100. Then that kind of brought the border up higher. So at least brings in that border here. So there it is. Continuity correction for p is x greater than or equal to 100 is the fact that we're going to look at p as x is greater than 99.5. Sweet. Okay, that's cool. Next is the z-score. You guys talk to me. Have you guys found the z-score yet? Or if you found it, tell me the z-score. Ooh, I got something a little different than that. I don't know if you used the 100.5 or used the 99.5.
Oh, I do not use the.
Gotcha. Okay. So I got 94 here. That's the average. The 99.5 is here. That's our little value here. So first of all, I'm looking at a positive z-score for sure. And then I want to go off to the right. That's the next thing that I need to do. Cool. And if I were to do that, I get a z-score of 99.5. Subtract 94. And if you want to still put in the previous solution to the standard deviation, you can do that. Or you can put in the value that we got. If you put in the value that you got of, what is it, 7.06 or something like that? Is that right? Yeah, 7.06. You might be off just a little bit, okay? Because that was an exact answer. So if you want to put in the formula the way we did it before, that's cool. So 0.78, which is true. It's positive because it's on the right-hand side of our average. Okay. Let's go with it either by table. Remember, your table always looks at less than values, right? So you're gonna have to do the opposite if you do it by table. All right, if you did it by table, All right, let's do this here. If you did it by table, you kind of look something like this right here. X is greater than or equal to 90, 9.5. Since it's a right tail test, you're looking at a Z value of greater than 0.78. And if that's the case, because it's right tail, you're going to look at the complement of it, right? Well, good. Does that make sense? It's the complement of that. So when you put it in, you should get a 0.7823. Hey, that's funny. And then subtract it from 1. So again, that's by table. Let's do it by calculator here. So in this case, calculator, that's cool because it does both right and left tails. So distribution number 2. Voila. And this time, since we're going off to the right, we're going to say 0.78 is our lower bound for our Z-score. 10,000 is our higher bound for a Z-score, 100,000, whatever. And our mu and our standard curve is 0. Our standard deviation is 1. And click enter. So 0.21769 or 0.2177, roughly 21.8%-ish. Okay, we good there. Boom, one more. So we did a left tail test, a right tail test. Let's do the one that's kind of like right in the middle. So study of the NFL retirees, here it is, 50-year-olds or older, found that 62.4 of them have arthritis. So you randomly select 75 NFL retirees who are at least 50 years old and ask them whether they have arthritis. What's the probability that exactly 48 of them say yes? This kind of harkens back to memory loss and concussions in football players, where the NFL did not recognize it at first. Okay, just go as far as you can. Go for it. You're going to have to do 2 Z-scores now. Notice what they're asking for. What's the probability that exactly 48 will say yes? Whoa, that's a little different, huh? Not going to the right. We're not going to the left. We're going to have a little slice in the middle. All right, give you guys maybe like 2 minutes here. Try to go as far as you can just by yourself, and then we'll do it together. So still following the same process here. The question is, do we meet our condition to use the binomial approximation? I think so. 75 times 0.624 is 48.8. That's pretty good, above 5. 75 towards the complement of 62.4% is 37.6%. Multiplying that times 75 gives us 28.2. Good. We can approximate using the normal distribution. Cool. Let's go from there. So the mu is what we calculated the first time, is n times p. Don't even need to recalculate it. Just put it down and be done. Next piece is the standard deviation. Hopefully you guys got something called 4.19. Check if you haven't, and correct the work if you need to. And then check me as well. Make sure I did not do any mistakes here. I don't mind being corrected. Okay, cool. So we've got that. And this one's a little bit different. This one says exactly 48. So probably exactly 48. Will say they have arthritis. All right, so the new stuff here. All right, if you want to, you can refer back to page 277. That would help. If you need to go back just to make sure everything's good. All right, so exactly 48 means all we're gonna do is we're gonna take half a unit more and half a unit less. That's all it means. So not bad. This is even easier than trying to figure out, do you include the C? Do you not include the C? We just take half a unit higher, half a unit lower. That's it. So exactly 48 really corresponds to this little nudge of from anything from 47.5, anything up to 48.5. That's all it means right there. Just one slice. So if you want to see a graph of it, there it is. The average is 46.8. That's the average that we have. And our probability is just going to be the slice between 47.5 and 48.5. So each one of these now we need to find a z-score. So now we have a lower z-score. We actually have an upper z-score. So let's do that. And then we'll jump from there. So a z-score corresponds to 75.5 would be 75.5 minus 46.8 should be a positive value. Divide by all that, and I'll calculate that. You guys just check, make sure you guys got the same I did. I got 0.17. Are we good with 0.17? So notice now we have a Z1, right? We have a Z1 and a Z2 now because we have two different Z-scores. Okay, go up 1 unit higher, so 48.5 minus 46.8. Divide by the same exact numbers that we had before. And voila, we get a 0.41. So really what we're doing is we're calculating the area between these two pieces. Oh, sorry, let's go back over here. Okay, everybody good there. Just make sure you guys got the same numbers I did, all yours. If you need to copy them down, I'll take a quick pause if need be. All right, and let's go with it. If you did it by the table, the way the table does it, here's what you would have got. You would have got the z-scores between 0.17 and 0.41. Again, the table always goes to the left, right? So you gotta grab your big z-score, subtract your small z-score. Here's your two areas of each one. You subtract them and you get yourself that area. We're gonna do it by calculator because that's the way we've kind of learned to do it. So let me jump to giving us the calculator. So on, clear everything else up. Distribution, here it is. Number 2. And the bottom z-score for us is 0.17. Now we're gonna enter both of them, comma. We're gonna go up to a 0.41, comma. And we have 0.1. So our mu, our standard deviation. And then on the TI-84s, you have something called paste. So just paste it. It's your lower one, your upper one, your mu, and your standard deviation. Click on paste. It pastes it back to the home screen right here. And we go for it. And we correspond to, hey, there it is. Very, very close to what we had. So 0.0916. So roughly 9%. 9.2% if you want to be a little bit more precise. All right, how many were able to do that all the way through? How many made it almost, made it halfway? Cool, okay, a couple, few. Good, good. Okay, so this is where we end with 5.5.